So you are welcome to this class. I want to be looking at another form of a series called the geometric series. Okay, this is okay now. So geometric series. In our last class, we talked about uh, the notion of series of real numbers. Okay, we have defined series of real numbers. Okay, as a series which you can get from the sequence of this form. Okay, that is, if you have a sequence of this form, so the n partial sum corresponding to this sequence is given as x1 to be a1, s2 to be a1 plus a2. At least s1 in this case is this first term here, and this s2 is the addition of the uh, two terms, the first two terms. So here also can have s3, which means a1 plus a2 up to a3, and we can do so up to xn. This Sn in this case is referred to as the nth partial sum of the sequence. So, but if you are to add from here to here, okay, looking at the fact that this n is tending towards infinity, it means after this an, there's another term called an plus 1, an plus 2, and it goes like that. Okay, so if you are to represent the term here, okay, it means the term will also continue to infinity. So we have defined this Sn here as the n partial sum of the sequence, okay, in a compact form as this. And because this n partial sum is also tending towards infinity as n moves towards infinity, okay, so it means this partial sum itself can become a sequence. And we have defined the sequence of this form as this too. Okay, so this is S1, S2, and this also goes to infinity. Okay, this S as it's going to, okay. So what this is telling us is that we have been able to formulate another sequence, okay, from the partial sum as this, okay. And then in our when we are discussing sequence of real number, we have discussed many notions about sequences, such as bounded sequence, convergent sequence, or divergent. Okay, we have also talked about monotone sequence, Cauchy sequence, and what have you. Okay, so all these notions in our last class we said will also be valid for this. Okay, and from there we show the convergence of this. We say if this sequence converges to a limit, let's say s. Okay, if this converges to s, so in this case we say that s is the sum of this series. Okay, assuming as this is going now, this converges to a point. Okay, we have said this sequence, okay, that s, which is the point of convergence, is the sum of this series. Okay, And we have been able to prove that if this sequence also converges to zero, then the entire sum, okay, will exist. Okay, and we have said the converse is not true. We give a case of that of the a sequence which okay, we have said if this converges, okay, this sequence goes to zero, and we have given it another corollary that says the converse is not true. That it is not true that if this sequence converges to zero, this Sn converges to its sum. Okay, and finally we discuss the divergence theorem. Okay, which can be used as the converse of the convergence criterion. So today we want to look at another form of series called the geometric series. So you will see let's so now I want to look at geometric series. Okay, so we want to look at that what form of series we have when we say geometric series. So here we consider a sequence of non-negative terms. What it means is that each term of this sequence, okay, is non-negative. Okay, what it means is that is all the items in this sequence can either be zero or a number more than zero. Okay, we can't have a negative number. Okay, so such that uh, the sequence this is equal to a1, a2, okay, and so on and so forth. Okay, and this is equal to uh, let's do it this way. This is equal to a term like this. This is equal to a. That is, you are letting this first term to be a, okay, and this second time will be AR. Okay, this is AR square, and this goes. Okay, so by comparison, we see that this the first member of this sequence is A, while the second term of the sequence is AR, and the third term. Okay, so and for which we can have x Sn, and Sn will be the sum of the nth time of the sequence. Okay, that means this will be this. Okay, and this will be AR n minus 1. Okay, as we want to add up the nth time of the sequence, okay, where in this case we need to say is positive, okay, and R is also positive, okay. So what we are saying here is that if you are able to get this, okay, so that will be a formula for finding the nth term of this, okay. So let's see how we can generate a formula for this, okay. Uh, Under the geometric series, we can find a formula for finding this, okay, in the following way. So we can say that let's call this equation 1. So multiply equation 1 by R. So if you multiply this equation 1 by R, okay, what we get is that this will be Rxn equal to AR plus AR square, okay. I'm multiplying R to this place, okay. This will be Rsn AR, okay. We have a single R here, okay. When another R is multiplied to this will be AR square, okay, and this will be equal. This will be AR cube, okay. Okay. So the nth term here will be ARN, okay. So up to this term. So now, so let's call this equation 2. Now subtract 1 from 2. Okay. So if you subtract 1 from 2, what do we get? Okay. Or we want to okay, you subtract this from here, or say subtract 2 from 1. Okay. Either way, this will be Sn minus Rsn equal to, okay, it's like subtracting this and this, okay. The first one will be this, and the next one, okay. Of course, you see this term is not here, so it will be this term, this and this will cancel out, this and this will cancel out, up to the term up before this. So in doing this, all this time will be cancelled out. Okay, let me use a different marker for this. This time, okay, all this time will be removed, and the only time that will be remaining will be this, okay, which is A minus ARN. So So this implies that we can factorize Sn out, so that this will be this. So, and we can factorize A out, so that this will be this. Okay. So, and our aim is to find the sum of the partial sum of the sequence. Okay. So in order to do that, I want to make this a formula. Okay. So it means this will be okay. So this formula is referred to as the sum of nth term of the sequence an up to infinity. Okay, so you will recall that now when we are making an assumption for the term in the sequence, we have said that this a is a non-negative term or a positive term, and this r is also greater than 0. Okay, but looking at this formula, we can deduce two things from here. Okay, the two things are that you know that this sequence will be convergent. Okay, that is, if we tends n to infinity, okay, how do we know whether the sum here, okay, we have a sum of this. Okay, so there are two things that must be obeyed. Okay, the first one is that when, of course, when r equal to 1 here, we see that this will be undefined, and because of that, we'll remove r becoming 1. Okay, so now, since r equal to 1 give us a boundary, okay, for this formula, okay, we now say from 0 to 1, we want to see what is happening to this series, to this sum of series, and from 1 to infinity, we want to see what is happening. Okay, so but here we see that if r is less than 1, okay, then 1 minus r raised to the power of n goes to 0 as n move towards a very large number. Okay, sorry. Okay, because the term r raised to the power of n goes to 0. Let me move this down. Okay, this is not on the. What you are saying here is this: if r is less than 1, then the term here, the term at the numerator here, okay, which is 1 minus r raised to the power of n, okay, equals to 1, okay, as n becomes large. Okay, for example, if r is less than 1, we have many terms for that. Let's say when r is less than 1, suppose that r is 2. Okay, suppose that r is 1 over 2. Okay, from here you see that this will be 1 minus 1 over 2 raised to the power of n. Okay, now as this n goes to infinity, okay, the term here will be going towards 0, and because of that, the main term that will be valid there will be 1. Okay, so that's what we are seeing here. Okay, this term here will be equal to 1 minus 0, okay, as n tends towards infinity. Okay, because if you find the limit of this, okay, when n goes to infinity, okay, putting the fact that this r is now half which is less than 1. Okay, so this goes to 1. Okay, so that is the assumption we are making here. Okay, and because of that, This formula now reduced to uh, this formula at infinity, okay, will be equal to uh, a. Okay, of course, it means the method here will become 1. Okay, so and when this value should be a times 1, that will be a, and this should be 1 over r. Okay, so in summary, what we are saying is this. In summary, if this if this are geometric series, with r less than 1, then the sum of the series is nothing but the sum of the series is nothing but this. Okay, so this is the formula for finding the sum of the series here. Okay, where a is the first term, this a here is the first term of the series, and this r is the constant ratio. So this r is the constant ratio. So what we are saying in essence is this. Assuming that we want to find the, of course, we'll look at other cases, okay, or let's conclude the cases. This is the case when r is less than 1, and we have said if you have to sum the series up to the very last term at infinity, okay, the formula is this, okay, for the case where the series is a geometric form, okay. But here too, if r is equal to 1, of course, the sum is undefined. It's undefined. Okay? That means if you look at from the original formula, okay, if r equal to 1, you see that, or put this r equal to 1 into the original formula, we'll see that, okay, the sum will be undefined because here we have 0 as the denominator. Now, in a case where if r is greater than 1, okay, then what we'll see that is that 1 minus rn, okay, you know, if this is greater than 1, okay, let's say a term 2, for example, as n goes to infinity, this will be becoming larger and larger. This time it will become larger, okay, and this one will give us a very big negative term, okay, converges to a negative largest number, okay. This is what this one gives us as n goes to infinity, okay. And what it means is that, okay, in some cases, let's say that we can have, okay, this converges to any of this, okay. In some cases where this will be positive, okay, when n is so what we are saying in essence is this: if r is greater than 1, okay, the sum of the series will be divergent. That is the meaning, okay. So let's see this now. So for any given series, okay, if R is less than 1, okay, what it means is that the series converges. 2, if R is greater than 1, then the series diverges. And the third case is if R is equal to 1. Okay, what we say is that no conclusion, no conclusion can be drawn. Or simply if R is 1, the series is undefined. Okay, so these are the three highlighted things we want to consider there. So now let's see some examples under the geometric series. Okay, so the first example here, we consider three series of examples. So if you have any question, you can put that down on the comment section. So I will respond to it. So let's see some examples here. So we will find some of the series. So I will find some of the series. Okay, let's see some of the items in the series so that one can have a picture knowledge of what the series actually is. Okay, when n is 1, so the first time here will be 1 plus when n is 2, it will be this. When n is 3, this will be 1 over 2 raised to the power of 2. That will be 1 over 4. When n is 4, this will be 1 over 8. Okay. The next thing will be 1 over 16, and this goes like that. Okay, so this is how this series look like. And what we are asked to do is to, although this goes to infinity, okay, but here we are asked to find the sum of the series. Okay, you know, as you can see, we don't know where it ends, okay, but we have to find the sum. Okay, so the convergence criterion we said earlier in our previous class can be applied to this. Okay. Okay, so if you're able to find the series of this and we can have a sum for this, what it means is that the associated sequence of this series, okay, converges to 0. Okay, one can apply that, okay, but that is not what we are talking about here. Okay, our concern here is to find the sum of this. Okay, so here you see that the first term A is 1, and the constant ratio here uh, is half. Okay, of course, this is less than 1. Since the constant ratio is half, okay, we can simply apply the formula that satisfies this case. Okay, you see, R is less than 1. Okay, so from there, you see that that series will converge. Okay, and you see this convergence, what it means is that this sum is finite and exists, or finite or exists. Okay, so let's see that. So therefore, the formula this will be so let me bring the this thing down. So therefore, using this formula, okay, so this will be equal to 1, as we said here that A is 1. Okay, so between this formula, this will be 1 minus half, and this will be equal to 1 minus half is half. Okay, and we'll find this. Okay, so what we are saying in essence is that if you have to sum this series, okay, to infinity, Okay, the sum is actually 2. Okay, so let us see this in the geometrical view. Suppose we have a rectangle. Suppose we have a rectangle of this form, whose length from here to here is 2. From here to here, the length is 2, and the length of that rectangle from here to here is 1. Okay, so you see that if from here to here is 2 and from here to here is 1, okay, we can divide this into this, okay, so that whatever is here, okay, all the sides of this will be 1, 1, 1, okay. So if you take the square of this, okay, so this is nothing but a 1, and this is also a 1, okay, so that's the square, okay. So now this term or this rectangle, okay, can represent this happy, okay. So the first square that we have here can represent